All right, welcome back, everybody. So last time we started talking about ridge regression. And with ridge regression, we had an estimator that looked as follows. So we said that the ridge regression set of weights that we would use would correspond to minimizing over all possible weight vectors the sum of the squared error between our predictions and our observed training labels plus some parameter lambda times the 2 norm, or the sum of the squared weights of W. And we also said that we could write the solution to this optimization problem as being x transpose x plus lambda times identity inverse x transpose times y. So what we didn't talk about is where this quantity lambda comes into play. So we talked about its role, we talked about its impact on the singular values of x, and how it affected what this matrix inverse looked like. But we didn't really specify how you would choose it. And so that's something that I want to touch on right now. So in particular, if we take all of our available, I'm just going to call it training data to start, but all of our data, then generally what we would do is we would split it into 3 pieces. So in particular, I would take the first, maybe 70% or so, and I would call this my training data. And then I would take another 15% or so, and this would be validation data. And then my final 15% or so would maybe be my test data. So all of this is coming from my original collection of data that I'm using to do my machine learning with. So what's happening here is with the training data, I am going to fit each possible model to the data, to the training data. Well, you know what, this is a little bit hard to read. Let me just put it up here. So when I'm using the training data, I want to fit candidate models. With the validation data, I'm trying to figure out which model is best. And then finally, with my test data, I'm trying to estimate how well whatever model I think is best will work on new data. So in the context of ridge regression, for instance, when I say, I'm using the training data to fit candidate models and the validation data to say which model is best, I'm really thinking here about different models corresponding to different values of lambda. So what I'm doing with the validation data is I'm saying I'm going to use it to select a good value of lambda in the context of ridge regression. And with the training data, what I'm doing is I am going to fit my W hat R, and I'll just put lambda in parentheses here to indicate that I'm going for different values of lambda, I'm going to get different values of this ridge regression weight vector. So for each value of lambda, I can use my training data to find a weight vector. And then with the validation data, I can use it to decide which value of lambda I think is the best. So let's map that out a little bit more precisely. Okay, so we're going to have our training set, which is going to be a bunch of xi yi pairs for I equals 1 to, let's say, m. And then for my validation set, I'm going to also have xi, yi pairs, but now it's for I equals, let's just say, m plus 1 all the way to n. So now what I would do is the following. I'm going to have a whole collection of different lambdas. I could call them lambda 1, lambda 2, all the way to lambda, I don't know, L. Just got a discrete set of possible lambdas that I want to consider. And so for each one of them, I am going to use my M training samples to find this W hat R for that particular lambda. So I'm going to get a whole bunch of W hat R's corresponding to different lambdas. And each of them is only going to be computed using my M different training samples. Then I'm going to measure the loss on my N minus M validation samples. So specifically, I might say that the loss on my validation samples for a given lambda could equal to the sum from I is equal to M plus 1 all the way to N of yi minus xi transpose W hat R lambda squared. So I'm just looking at the sum of squared errors on my validation data set. And when I am using ridge parameter lambda, then I'm computing the loss associated with that parameter, L lambda. And then finally, I would choose the lambda with the smallest L sub lambda. Now, in practice, when I'm doing this, I don't always know what the right range of lambdas is. If I see that I'm getting the smallest loss with the biggest lambda or the smallest lambda, I always feel a little nervous. I think, oh, well, maybe if I had gone even smaller or even bigger, I could have done even better with my loss. So I try to make sure that my grid is such, or the selection of lambdas that I'm considering is wide enough so that I'm actually choosing something somewhere in the middle and not on the edge. Just to make sure that I didn't narrow my search too artificially. And then in the context of the training and validation and test split, finally when I'm done, when I have chosen my lambda, so let's just call that lambda, lambda star, the one that gives us the smallest loss on our validation set. Once I have that, then I can estimate my loss on the final test data for this W hat R for lambda star. So I'm not touching my testing data until the very end when I've selected all the parameters, in this case lambda, and weights for my method. So you could even imagine, somebody holding this back. You don't get to look at it at all until you've done everything you can to figure out what the best possible method is. And then you just test and see how well it's working. This is how, for instance, a Kaggle competition would run. If you are looking at that test data before this stage, say using it to rethink what the best possible lambda is, then you run the risk that this test error will be artificially low because you've used it to make decisions, so that when you actually deploy your method in the wild, you're getting higher errors than you anticipated. So it's very important to keep this separate until the very, very end. Are there any questions? Yeah.
Wait, if the validation is going up to n, and n samples, where do we find the test data from that?
Oh, okay. Let me just say NV for validation here. And then my test data would be xi, yi for I equals n validation plus 1 all the way to n. Yeah. Any other questions? Yeah.
Like the optimization or the objective function, is that just like traditional squares?
Yeah, this is just the squared error, and I'm using squared error in this description here because that's also the loss that we've been using for ridge regression. But in general, you can use a variety of different things here. For instance, if we were doing classification, we said that we might train a classifier, find a set of weights by minimizing squared errors. But of course, what we actually care about is how many mistakes we make. We didn't use that number of mistakes loss because it's not clear how to optimize it. But when we're only looking at that loss on a discrete set of parameters, we can do it. And so in some cases, people will have a different measure of loss that they consider during validation than they do during training, because we're really typically in validation only considering a discrete set of options, so we don't have to worry about whether it's differentiable or convex or anything like that. So you've got a little bit of flexibility here. This is a design choice.
I'm just wondering why it wouldn't be like the smallest value lambda, because when you're figuring like the ridge regression like function, wasn't it the least or this minimizing these squares, but also like the extra term?
Right. So when we did the ridge regression, we were saying if somebody gives you a lambda, then what's the right weight vector? So what I've been doing here is I've been writing lambda in there. So for every different lambda you give me, I would give you a different weight vector coming out of ridge regression. And so now what we're talking about is saying, how do I choose which lambda I want to use? And that's what this process on the middle board is about.
I'm just wondering if like the left side of the argument is the same as the loss function.
Oh, I see. So you're saying here, when we are doing training, we are minimizing this overall function. And semantics or nomenclature varies from paper to paper. Some people would call this a regularized loss because I have a loss plus a regularizer. So they would distinguish, they would call this squared error the loss and this something different. Other people would just call this whole combined function that we're minimizing the loss. So they would use loss in a way that encapsulates regularization, just varies from paper to paper and person to person. But you are right that during training, I'm talking about minimizing this sum, whereas in what I mapped out on the middle board here, we are only looking at the sum of the squared errors. So I'm not considering the regularization here. Yeah. Any other questions? Okay, so then with that, I want to switch gears and talk about a setting where we don't necessarily have a regularization parameter, but we still have to deal with the fact that least squares will not work. So I want to talk in particular about an alternative to ridge regression that specifically is of interest when some of our singular values are equal to 0. So when some of the singular values are equal to 0, we said one of the ramifications of that is that there are many different weight vectors that we could find that perfectly predict our labels. So the question is, if I've got many different weight vectors and they all give me perfect predictions of the labels, or maybe even not perfect, but just equally good, then I have no way of distinguishing among them, right? So how do I choose which of these different weight vectors I want to use, right? So we said with least squares, well, we're just going to totally sidestep that. But now we're going to look at an alternative approach. And so specifically, we are going to define the pseudo-inverse of a matrix. And I'm going to start by defining it for diagonal matrices, sigma. And we're going to denote that as sigma with a plus sign, superscript. So this is not transpose, this is pseudo-inverse. And if we look at one of the diagonal entries of that pseudo-inverse, sorry, I'm going to do it like this. I compute the pseudo-inverse, and then I look at the diagonal entry. Then it is going to be 1 over the original singular value if that singular value is greater than 0. But if the singular value is just equal to 0, then instead of trying to divide by 0, I'm just going to say in this pseudo-inverse matrix that the corresponding diagonal entry will just be exactly 0. So in other words, it corresponds to taking the transpose of sigma and inverting the non-zero diagonal entries. Which I think I didn't fully specify. So let me give you an example that's a little bit more concrete here. So let's look at the special case where P, the number of features that I'm trying to learn from or use as predictors, is greater than N, the number of training samples, and X has N linearly independent rows. So before we were talking about settings where the number of samples was greater than the number of features, and X had P linearly independent columns. And in that case, we could do least squares. So now we're going to consider the setting where we actually have lots of features and all of the different training samples, all the different feature vectors for the different training samples are linearly independent. So pictorially, our matrix X here is now short and fat. It is N by P. And if we think about its singular value decomposition, U is N by N, and sigma is N by P, and V is going to be P by P. And so now, if we were to think about the pseudo-inverse of sigma, then first of all, let's think about what sigma looks like. It's going to have entries sigma 1, sigma 2, all the way down to sigma n. And then the remaining n minus p columns will all be equal to 0. And so now if we were to compute the pseudo-inverse of that, then what I will have is something that's p by n. So I'm going to have 1 over sigma 1, 1 over sigma 2, all the way to 1 over sigma n, and then all zeros. So this is my pseudo-inverse. And so now what I can do is I can use this pseudo-inverse to form a predictor. So specifically, I'm going to say that my pseudo-inverse predictor, W hat, is going to correspond to taking this V matrix times sigma pseudo-inverse U transpose times Y. So I want to say a couple of things here. So first of all, I want to emphasize a point that is going to be helpful to us later in today's class, which is that this pseudo-inverse here is equivalent to writing sigma transpose times sigma transpose inverse. So I've got an explicit formula for this pseudo-inverse. In addition, I can show that what I'm writing here, this pseudo-inverse predictor, I can write explicitly in terms of x. This would be x transpose times x transpose inverse times y. So we can define the pseudo-inverse of a general matrix X using the pseudo-inverse of its singular value matrix, as I've described. I also want to compare this with least squares. So with least squares, we had a weight vector that we derived to be V times sigma transpose sigma inverse, sigma transpose U transpose Y. And we can also compare with ridge, where we had W hat ridge was equal to V times sigma transpose sigma plus lambda identity inverse sigma transpose U transpose times Y. So now we've got three different expressions for three different weight vectors that we can use to fit our training data. So one thing I want to emphasize when we look at these is that they all have a very similar form. All of them start with this V matrix. All of them end with U transpose Y. And the thing that's really distinguishing them in the middle is what we're doing with the singular value matrices. So with the pseudo-inverse, we are only inverting the non-zero singular values. With least squares, we end up inverting all of the singular values, which is why we can't use it everywhere, because sometimes singular values are equal to 0, and when we try to invert them, we get major problems, as we talked about last class. And with ridge regression, we are adding a little bit to all of the singular values that we invert, so when they are 0, we don't have huge blow-ups. We're not dividing by 0 anymore. And so these are three different ways of handling the singular values of X in order to get good predictions of weight vectors that can then help us make good predictions of labels on new test data. Are there any questions so far? Yeah.
Just to make sure that equivalence is true, the sigma transpose sigma transpose inverse, that's true in every case, not just a special case, right?
So I think this particular equation here is for this special case where I have P greater than N and N linearly independent rows. So when I've got N linearly independent rows, then this matrix, sigma, sigma transpose, is invertible. But in general, it might not be. And so I think that the form of that pseudo-inverse can look different depending on the setting. And personally, I find it most intuitive and general to think about it like this, to think about inverting the non-zero singular values and taking the transpose. And I can do that for a matrix of any, or for a singular value matrix, regardless of the dimension, how many rows it has versus how many columns, and whether or not, and regardless of how many singular values are 0 versus non-zero. So this I can always do. Yeah.
When can we use this pseudo-inverse like predictor? Like, can we use it like for, like, is that like just a new method, or can we use it for ridge regression?
So the pseudo-inverse predictor is not ridge regression because the ridge regression explicitly has this lambda parameter in here that's not equal to 0. So it is doing something different. At the same time, it is conceptually very similar in the sense that in both the pseudo-inverse setting and the ridge regression setting, we potentially have more than one weight vector that could be equally good fits to our training data. And we are, through these choices, deciding which weight vectors we are going to give preference to. So I'm going to talk a little bit more about the pseudo-inverse in a second. But with the ridge regression, we are explicitly saying that we want this balance between squared error and the sum of the weights in the weight vector. So that is conceptually very similar to what the pseudo-inverse is doing, but they are not the same thing. Yes?
What's the subscript on that pseudo-inverse?
Oh, for the pseudo-inverse here, the subscript is II, just indicating it's the ith diagonal entry. Yeah. Yes?
Would the pseudo-inverse predictor P smaller or equal to that?
So we can use the pseudo-inverse predictor in general settings, but it won't always have this particular form because X transpose is not always invertible. But we can always take the SVD of X, compute the pseudo-inverse of sigma, and have this predictor. So this is just to be clear, this here is very general, and this is specific to when XX transpose is invertible, or X has n linearly independent rows. Does that make sense? Yeah, great question. Yes?
What is the incentive behind using this pseudo-inverse method?
Perfect. Right, we are going to talk about that right now. So what exactly is it doing? So the claim is the following. So let's consider the case when X has n linearly independent rows. And in that setting, we have that the choice of this pseudo-inverse predictor, W hat, I'm just going to say W hat, equaling U sigma pseudo-inverse, V sigma pseudo-inverse U transpose Y, has the smallest norm. So the 2 norm of W hat is going to be as small, the smallest possible norm of any W satisfying our training labels y equaling x times w. So in this setting, where I can fit my data, my training data perfectly, where there are many different weight vectors that can perfectly predict my training labels, of all of those weight vectors that give me perfect predictions, the pseudo-inverse is going to give me the one that has the smallest sum of squared weights. Okay, so let's actually see how to show that. If we just consider any weight vector w, I can write that the norm of that w that I choose is equal to the norm of w minus w hat plus w hat, like that. Okay, now I'm going to split this up, and I'm going to say this is equal to w minus w hat, 2 norms squared, plus 2 w minus w hat transpose w hat plus the 2 norm of w hat. So once I've written the norm of any vector w this way in terms of the norm of my pseudo-inverse, then I can start to think about my machine learning context. So let's assume that this w is giving us a perfect fit to our training labels, and so it's just as good as w hat. Okay, so we are interested now in knowing, well, what's special about w hat compared to w? Both of them are equally good predictors of the training labels. And my argument, or my claim, was that w hat is going to have a smaller norm than w, that it's got the smallest possible norm. So this assumption means that if I were to look at the product of x, w minus w hat, then that has to be equal to 0, right? Because xw and xw hat, they have the same value. So if I subtract them from each other, then I just get 0. And so if I think about this middle term here inside my expression above, then what I get is that w minus w hat transpose w hat. I can write that as w minus w hat transpose, and now I'm going to plug in my expression for w hat, which in this context we're going to use the version written in terms of x is x transpose, xx transpose inverse times y. But now what I have here, if I just group this w hat transpose with the x transpose, I know that that has to be equal to 0 because that's what I have up above. So in other words, this is equal to x w minus w hat transpose times xx transpose inverse y. And this whole thing here is 0. And so this whole thing is 0, which tells us that that whole thing is 0. So if we put that together then, what we have up here is that the 2 norm of w is going to be equal to the norm of w minus w hat plus the norm of w hat. So when I look at this, I know that all norms, they correspond to like links of vectors, they have to be non-negative. So if w and w hat are different, if they're not equal to one another, then this norm is greater than 0. And so this tells us that the norm of W has to be greater than the norm of W hat. So just some very simple algebra is showing us that when we compute this pseudo-inverse predictor, then any other predictor that we might find, W, which also gives us a perfect prediction of the training labels, would have to have a bigger norm. Or in other words, the pseudo-inverse predictor is going to have the smallest norm among all predictors that perfectly predict my data. Yes?
How is that initial assumption different than just saying W equals W hat?
Oh, right here?
Yeah.
So that's a great question. So I actually was going to work through a simple little example right now that I think will get at that. So in this example, x is going to be 1, 0, and then 0.1, and then 0, 1, 0. So I've got 2 rows, and those rows are linearly independent, just like in our setting. And our y vector of labels is going to be 1 and 0. So now there are actually multiple different W's that could fit this, right? So possible W's. We could have 1, 0, 0. So if I were to assign weight 1 to the first feature and 0 to the other features, then I will get a perfect predictor of y. But there's other W's that I could also consider. For instance, I could have 0, 0, 10. So I could say instead of giving weight 1 to that first feature, I could give weight 10 to the last feature. That's going to also give me a perfect prediction of the labels. Or I could do any combination of those. I could do negative 1,000, 0, and 10,000. Negative. I think negative 999, right? And so I have multiple different ways that I can combine these two different features and get exact predictions of y. And so for all of these W's, they all have the same XW, and that XW is equal to y. So assuming that the XW's are equal is not the same as assuming that the W's are equal. And so that's why we have to make that distinction in the proof. And what we're saying here is, among all these different candidates, this weight vector here has the minimum norm. So it's a choice, right? We're saying that there's infinitely many possible W's that could perfectly predict our training data. And we, as machine learning designers, have to make a decision about which of the infinitely many W's we prefer. And minimum norm is one particular choice that you can make. But, depending on your context, you might say it's a little bit silly that I've got two features that are both really predictive of y, and I'm artificially choosing one versus the other just because the raw values or the normalization is different. And that's a fair criticism. So there are many different ways that people address this, different kinds of regularizers besides ridge regression. that you can use to disambiguate between candidate models that all fit your data well. But the minimum norm is one that's been around for a long time and is extremely relevant in many different settings and worth knowing about. Yeah?
Sorry, I kind of zoned out for a second, but we want to choose a weight vector with the minimum norm, right, to avoid really large weights because that causes overfitting, right? Is there a situation where we want really large weights?
Right. Question is, often we like to avoid having large weights to help avoid overfitting. Are there settings where we really want large weights? Nothing's coming to mind at the moment. What I do see a lot are things where people will say, I want, so alternatives to this would be to say, I want sparse weights. So here, let's just talk about alternative regularizers. So one would be to say, let's minimize the norm, or relatedly, try to make, minimize the norm. We could also say, make whatever W hat we choose sparse. So we want to have as many 0 elements as we can. So we'd be saying, instead of sharing the weights among lots of different features, I just want to choose a small number of features that are good predictors. That's another possibility. Sometimes people will say, make W hat smooth in some sense. So maybe there's some ordering to my features. Like, for instance, they correspond to pixels in an image or something, where somehow I think the weight for one feature should be related to the weight of another feature. And so what I might do then is I might say that I want the ith element and the I plus 1th element to be closer if possible. I guess I'm just saying absolute value. So again, these are just all design decisions that would depend on the context of your problem. And depending on that context, any of these can make a lot of sense. And of course, there's hundreds of other regularizers out there. But these are some of the ones that I see most often. Yes?
So, is the, conceptually, can we think of the non-invertibility of, it's that X transpose X, and the fact there's multiple possible outcomes as like linked, and with ridge regression, because we're favoring an outcome that also solves non-invertibility and vice versa?
Yes. So in this setting, this particular X, we have, P features, and they are linearly dependent. And so, as we've talked about before, X transpose X is not invertible. And there is also no unique least squares solution. Right? So there's multiple different weight vectors here. They give me the same sum of squared errors, which is 0. So there's no unique least squares solution, and that's intimately related to the fact that X transpose X is not invertible. The reason it's not invertible, the way to think about it not being invertible is that there is no unique solution here. And this is because my P features are linearly dependent. So these are the settings in which we need to use some sort of regularization or impose some sort of structure on W to help us choose among possible weight vectors that all look equally good, more or less, in terms of prediction on the training data. Yeah?
This might be too much of a digression. Is there what is the difference between having a
Okay, so what's the difference between a sparse W hat and just minimizing the weights? This is subtle, but I'm not going to have a great example off the top of my head, but I could imagine having a W hat where my entries are, I don't know, let's just say 1 and then 0.01 and 0.02. So in this setting, with this vector, these two entries here are not really contributing a lot to the norm. And yet I'm giving the corresponding features some weight. And so if I try to promote sparsity, what I'm doing actually, or the way that people do this most often, is they try to make or minimize the L1 norm of W, or the sum over I of the absolute values of the weights, as opposed to the squares of the weights. So those are different. And when I try to minimize this L1 norm, as opposed to minimizing the Euclidean norm that we typically are working with in this class, then I'm trying to say, you know what, if I can get almost as good or equally good predictions from a weight vector where I've only put weight on one feature, then in some settings that I would really prefer. For a variety of reasons, one of which is interpretability. If I want to say, hey, I want to know which features I really should care about for predicting labels, then this can highlight a small number of features that are highly predictive in a way that we might not get if we just try to find a minimum norm solution. Yeah.
But what is that expression? Is that like Wi hat minus Wi plus 1 hat?
Oh, sorry, I guess I don't need the vectors here. I just mean if I've got a weight vector and I'm looking at the ith entry and the next entry, two neighboring entries in the vector, then this smoothness condition would be like saying that they have similar values. Yes. Sorry.
I mean, like, doesn't like sparse mean like as many 0 elements as possible? So, like, even the elements have similar values, that's not like the same as sparse.
Yeah, these are two different bullets. Sorry if that's not obvious. So one possibility is to minimize the norm, like we've been talking about, or use ridge regression, which is closely related. Another separate possibility is to try to make W sparse. And a third possibility is to make it smooth. So you're totally right. They're not the same. Yeah.
When we were talking about geometric meaning, like the singular values, they were like directions of like most variance. So like, what's the meaning of like taking the pseudo-inverse of those? And like, I guess like, how would you map that concept of like having the minimum points as well?
Okay. So the first question was, is there a good geometric interpretation of the pseudo-inverse? It's a great question. I'm not sure. I need to think about that a little bit. Yeah, I'm not sure. But in terms of thinking about, I think the second part you were saying, how do we think about minimum norm versus sparsity? Is that right? Okay, so here's one way that I could look at it. Imagine that I've got my space of possible weights. So now P is equal to 2. So my weight vectors have entries W1 and W2. And then I can say, in this setting, where there are many weight vectors that all fit my training data. So I'm going to draw a line here, like this. So for every point on this line, xw is equal to y. Okay, so these are all possible weight vectors that fit my training data. And now my job is to choose among them, right? All right, so there are a couple of ways I could do this. One is I could say, I want to have the minimum norm. So now I can think about the space of all weights that have equal norm. And so maybe I'll do it like this. So this red circle, every W on this circle has the same 2 norm. They're all the same distance from the origin. And so when I look for a minimum norm solution, what I'm going to choose is this one here. So this would be my W hat. I'm going to write MN for minimum norm here. And alternatively, I could say I want to think about all of the weight vectors that have the same L1 norm, or the same amount of sparsity. And that is going to look so that, well, it's not exactly sparsity, but the L1 norm. That turns out to be a diamond. So now every W on the diamond has the same L1 norm, or the same sum of absolute values. And so if I say, among all of the possible weights that fit my training data, I want to choose the one that has the minimum L1 norm, then I would choose this one. So this would be my W hat. Let's call it sparse, because that's how I've been referring to it. So depending on the norm that I choose, I may be choosing or preferring different weight vectors that fit my data. Does that answer your question? Okay, yeah, it takes a little bit of thought. It's not quite as easy to grasp, for me at least, as like the least squares geometric picture that we drew. Yeah, I'll come back to you. I want to make sure you hear others too. Yeah.
Can I think sparse? W is related to truncated SVD, where some of the singular values you set them to be 0. So like some features are not used.
So with the truncated SVD, we took some singular values and we would set them equal to 0. And in general, we would set the smallest ones equal to 0. If I think about the pseudo-inverse, I'm taking the smallest singular values. Maybe you could think about it as inverting them and then truncating some of the biggest ones after inversion. But it's a little bit different. Yeah. Yes.
So for sparse, do we mean as 0, like as many 0 as possible, or do we mean the least, like L1? Because like here for the like white diamond, if we just want as many zeros as possible, then we can take the point that's like anything on the y-axis.
That's right. So I did not. Yeah. So we could say conceptually that what we would like to promote is sparsity, as many zeros as possible. But then when it comes to developing algorithms where we can actually solve the optimization problem, explicitly trying to give us sparsity turns out to be computationally hard. And so as a proxy, we will try to minimize the L1 norm. It's totally analogous to what we were talking about with matrix completion, where we might like to minimize the rank of a matrix, but computationally that's hard. And so instead, we might try to minimize the nuclear norm of the trace norm. So same here. We might care about sparsity on a conceptual level, and yet when it comes to practical algorithms, working with the L1 norm is much easier. And under certain conditions that we're not going to be able to go through in this class, you can prove that minimizing the L1 norm is equivalent to maximizing sparsity. But again, beyond the scope of this class. Yeah.
Actually, I wanna ask a question about previously we've actually learned a lot of techniques on how to make linear dependent columns to be define a basis, which is linear independent. Why do we have different features which are linearly dependent, but we are not, for example, to drop out some of the ones who are making it dependent? Why we bother to use a new technique instead of just making it linear independent, find a basis, and then use the previous one that we have.
So it's a fantastic question. And for the recording, the question is, if I've got P features and they're linearly dependent, why am I going through all this rigmarole? Why don't I just do PCA, find a basis for the features and work in that basis space? And that is a totally valid way to go. One reason is interpretability. So here, my features mean something very concrete. And when I learn weights on those features, I know how to interpret it. This is telling me if I want to have a good prediction of Y, then I should just look at the first feature and I can ignore the other two features. I can interpret this weight vector that way. But if I were to instead first learn a basis, well, this isn't a great example because the basis would give the same result. But in general, the basis is going to be a linear combination of all the features. And so if I learn a basis, and then my predictor says, oh, you should put a weight of 5 on your first basis vector, which represents some combination of all your features, then that gives you good prediction, but is not necessarily interpretable in the same way, right? It's not telling you which of your raw features are important. So it really is context dependent. There are definitely settings where just doing some dimensionality reduction, finding a basis for my features, is perfectly legitimate and a great way to go. And then there are other settings where we really do care about interpretation, and these alternative techniques that we're describing are a better way to go. Yeah. Okay. Really excellent questions, everyone. Thank you so much. So the next thing we're going to do is transition to kernel regression. And this is going to lead us directly to the support vector machines, which before neural networks became a big thing, were the workhorse of a lot of machine learning. So this is extremely important conceptually. It's going to teach us a lot of important ideas that are still in use today. So recall that what we've been working with is predictors of the form y hat is equal to just a weighted sum of my features. So in my toy example here, let's just say I've got 2 features. So my y hat might be some w1 x1 plus w2 x2 plus w3. And I can write this as W transpose X, where in this case, my X is equal to X1, X2, and then I've tacked on a little 1 at the end here. Okay, so this is sort of the linear prediction setting we've been working in. But we've noted before that what we might prefer is something like this. Let's say, quadratic predictor, where y hat is, say, w1, x1, w2, x2, w3 time, and then I could have, in addition, x1 squared, w4, x1 squared, and w5, x1, x2, and w6, x2 squared. Right, so there are settings where this would be a mechanism for getting much higher accuracy. And so what we would like is to figure out a way to make this systematic. So first of all, let me provide a motivating example. So imagine that when we plot our training data and we look at our 2 coordinates, we see something like this. So we see all of our all of our positive samples in a little disk here. And then when we look at all of our negative samples, they lie in a ring. Okay, so we as humans can look at this and immediately recognize that there's a very simple way to differentiate the red and the blue samples. If I restrict myself to a linear classifier, there's no linear classifier here that's going to work well. No matter where I put that line, I'm going to be making errors. And so by allowing ourselves to have quadratic predictors, then what we can do is learn decision boundaries that can perfectly separate our data. And the way to think about it is like this. So I'm going to redraw this data, but instead of drawing it in 2 dimensions, like I just did, I'm going to add a third axis. So I've got x1, x2, and then my third axis here is going to be x1 squared plus x2 squared. Okay, so a combination of some of the features in this quadratic expression. So now if I plot my data, my training data in this setting, then I get all of my red dots here by the origin, and I've got my blue ring up here because they're farther from the origin. This is like a circle that's on its edge. I know it's hard to tell from the drawing. And so once I've mapped everything into this 3D space, it's very clear that there's a nice linear predictor in this new space. So what we're talking about is saying, hey, we've spent all this time on least squares, minimum norm, pseudo-inverse, ridge regression, etc., but it only is for these linear predictors, and there's lots of settings like this where we want nonlinear decision boundaries. And the point I want to make is that there are times where we can just augment our features, like I've done here, so that in this new feature space, I can just use all of the linear prediction tools that we've been learning about all quarter and get very accurate and powerful predictors. Okay, so in general then, what we are going to do is we are going to define a function phi that will input a feature vector x and output a new feature vector that's going to look like, in this case, x1, x2, I guess 1, x1 squared, x1, x2, and x2 squared. And so now what I'm saying is that I want to have my y hat, my prediction, be equal to the inner product of this phi of x and some weight vector. So I'm still now, after doing this mapping with phi, doing linear prediction. I'm just doing it with the phi feature vectors instead of my original x feature vectors. Everything clear so far? Okay. Very simple concept, extremely powerful. So when we talk about using kernels, what we're trying to do is to formalize and generalize this concept. So you might be thinking, well, what is there new to learn here? I can just define one of these phi functions and then proceed with least squares or ridge or whatever else. But the problem is that if x is in, let's say, each feature vector is in p dimensions, and we say that our new feature vector phi of x is in d dimensions, then d is typically way bigger than p. So for instance, if we had quadratic polynomials, the way I described on the previous board, then D is on the order of p squared. And if we were to have fifth degree polynomials, then we have D is on the order of p to the fifth. And if we think about p, the number of features being, say, in the hundreds or thousands, then taking these to huge powers is going to create just enormous feature vectors. And then we run the risk of overfitting and some of the other challenges that we've talked about, as well as computational challenges. And so with kernel methods, we are going to basically let us make predictions of the form y hat is equal to the inner product of x, or phi of x, and some weight vector w. And we are going to do this in a way that helps us avoid overfitting and with manageable computation. Okay, so in particular, what we are going to do is we are going to do, the first thing we're going to do is we are going to do ridge regression using these phi of x feature vectors. And typically, when we talk about these phi of x's, we'll refer to them as being in the high dimensional feature space. Because often the dimension in this phi, after this phi mapping, is much, much bigger than our original dimension. So we think about phi as mapping our original features to some new high dimensional feature space. Okay, so now I want to think about what happens with ridge regression and add a little bit of nuance that we didn't see last time, but which is going to be really helpful now as we start thinking about kernel methods. So first, if we recall ridge regression, again, we said that our weight vector w hat r looked like v sigma transpose sigma plus lambda identity inverse sigma transpose u transpose y. And I want to focus on what's happening with these singular value matrices. And so in particular, the point that I want to make is that this is equivalent to, we just haven't written it this way before, sigma transpose, sigma transpose plus lambda identity inverse. Okay, I can write it either way, and they are the same thing. I'm using the fact that the sigmas are a diagonal matrices. So I'm not going to show this in every case, but for example, when n is less than p, when we've got huge number of features compared to the number of training samples, which can happen easily once we start mapping to these high dimensional feature spaces, then our sigma, which is n by p, so it's going to be short and fat, is going to have sigma 1 through sigma n, and then everything else is 0. And so now if I look at sigma transpose sigma, I'm going to get something that is p by p. And so I will have sigma 1 through sigma n. And then I will have a whole bunch of zeros for the rest of this diagonal matrix. And so then if I were to, from here, compute sigma transpose sigma plus lambda identity inverse sigma transpose, then what I would get would be sigma 1 over sigma 1 squared plus lambda all the way to, at least we can get this right. Yeah. Sorry. Apologize. This is sigma. Right. Okay. This goes up to sigma n, but this is p by p. And so now here I've got something that is p by p times something that's p by n. So the product is going to be p by n. And so I'm going to have something that's taller and thinner. And I'm going to have it be all the way to sigma n over sigma n squared plus lambda, and everything else down here is zeros. Okay, now if I look at the equivalent thing that I mentioned here, then I am going to first look at sigma transpose plus the lambda times the identity. And what I'm going to get now is that this is going to be n by n. And so I will have sigma 1 squared plus lambda all the way to sigma n squared plus lambda in a diagonal matrix. And if I compute sigma transpose times sigma transpose plus lambda identity, I end up getting exactly what I showed you before, sigma 1 over sigma 1 squared plus lambda, all the way down to sigma n over sigma n squared plus lambda. And everything else here is just going to be 0. And the dimensions line up because this is n by n, and this is p by n, and so my product here is p by n, so it's exactly the same. Okay, so key point here is that now I'm just going to write this expression using this alternative way of formulating ridge regression, and that's going to be very helpful as we start thinking about how we can use different kernel methods. Okay, so when we look at our ridge regression estimate, we've got V sigma transpose, and then I'm going to leave a little space. Then I've got sigma transpose plus lambda identity inverse, and then I've got U transpose Y. And now what I'm going to do is insert in the middle of that a U transpose U. And I can do that because I know that this is identity. But this is helpful because now I can say, hey, this first product here, this is just exactly the same as X transpose. And everything else, including the Y, I'm going to just call alpha. Okay, so I'm saying now that I can write my ridge regression estimate as X transpose times this vector alpha. And this is important because it tells us that W hat R is equal to a weighted sum of the columns of X transpose, which is the same as a weighted sum of my different xi's. And the alphas tell me the weights. So this alpha vector is going to be an n-dimensional vector. So alpha is telling me how much weight to give to each one of my training samples. And then I'm going to write my weight vector for ridge regression as a weighted sum of those training samples. So here are the training samples, and here are the weights assigned to each one of them. And I've got this formula here that tells me exactly how to compute those weights using my training labels and the singular vectors and singular values associated with X. So now we can say that we want to compute ridge regression in our feature space. So specifically, we are going to define a new matrix, capital Phi, which is simply phi of my first training vector transpose, and then phi of my second training vector transpose, all the way to phi of my nth training vector transpose. So this matrix is n by d. It's got the same number of rows as X did, but way more columns. And now what we're going to do is we are going to say that our ridge regression estimate is going to be the argmin over W of y minus capital Phi times a weight vector, 2 norm squared, plus lambda times the sum of the squares of all the weights. So now this is framed in a way that we know how to solve. We've spent a couple of weeks talking about this now, maybe 1 week. So we can, maybe 2 days. But now we have tools for approaching this. But what we're going to see next week is that we can use what I described here, the fact that this weight vector is a weighted sum of the samples, to get an alternative expression for this ridge thing that, like I said, is going to allow us to compute things very efficiently. So in particular, what's going to happen in many practical scenarios is that this phi matrix, the number of rows D is going to be enormous. We are going to want to not even have to compute this phi matrix at all. So we have to say, all right, this is ideally what we would like to compute. How can we compute it in a way that totally avoids computing this matrix and uses the information that we have derived about ridge regression in order to make that computation feasible? So that's what we will talk about in detail next week.